that is going. YouTube.com tea leaves programming. And with luck, all we'll see. Okay, we are not yet live. It's telling me there's a connection. So it thinks we're streaming here, but it's not actually. Let's see. Maybe I need to do it from here. Channel dashboard. Content. Live. Okay. Live now. I bet. Oh, I have it turned to private, so that's okay. So let me change the title. Von Neumann. It is Neumann, right? Like.
Yeah, Neuma, two N's. I think like the microphones.
Okay.
But, just in case you ever feel useless, you can note that he both invented the still dominant model of computation and quantum physics.
Before he was 28, probably.
Not not so much quantum physics, but the current mathematical framework for it is really him. So
Okay, so I see it.
okay.
I see a thing. Let me see if I can actually watch it.
Okay.
I see a thing. I hear both of us. I can actually watch it. Say, count to 10.
1, 2, 3, 4, 5, 6, 7. Cool.
Gotta remember to unmute. Okay, so we now have the splash screen up. It says it starts at 2. So go to the bathroom, get yourself an apple, a drink, whatever you want. I'll see you back here at like 2 minutes to 2.
Okay.
And I would mute your mic, so we'll do a mic check when we get back. See ya. And just leave your video up. Your video is not visible. That's only visible to me.
Oh. Hmm? Can't get it in focus. Yeah.
It honestly looks like it was being censored, like the mug had something inappropriate on it. But
Yeah.
this
It
is a
has to be,
family stream, so
yeah. I guess it has to be right where my head is. Otherwise, the blur filter takes it out.
oh, that makes sense. Well, we've got about 2 minutes before we begin, and a couple people on the stream already. Welcome to both of you, and looking forward to having a good conversation. Now, the trickiest thing for me as I do this, of course, is we are going to be visible in the camera, and but I'm looking all over the screen trying to operate the stream. So I apologize in advance if I seem to be gazing off into the distance.
So the paper was published in 78, but it's based on a lecture from 77. So both years are right.
Oh, thank goodness.
Because he got the Turing Award in 77, which is where the paper came from. It was his Turing Award lecture.
It's nice to know that I didn't completely imagine the 1977
Yeah.
date. One more minute and then we will begin. I feel like since I told people 2 p.m., I don't want to
Yeah, that's
formally start. On the chat, Nathan says he's scheduled his day around this, so no pressure. All right. Hello, everyone. My name is Pete Berger. This is Pete Sue. And
Oh,
we formerly used to do blogging back when blogging was a thing, but now all the cool kids are doing YouTube, so that's what we're doing. We wanted to talk about a paper today, and that paper is John Backus's 1977 or 1978 paper, Can Programming Be Liberated from the von Neumann Style, a Functional Style, and its Algebra of Programs? So, Pete, if I can give a little bit of introduction and then ask you a question about this. So, our original plan was to do another of what we called Zero Page, which is like looking through old Byte magazines and kind of laughing at the advertisements. And then you suggested this. So, where did that come from? That impetus?
Oh, I don't actually remember. I think maybe you mentioned our mutual friend Patrick, who is a well-known functional programming enthusiast, and this this paper, in some sense, although as we'll see, what it proposes doesn't really turn out to be how functional programming really turned out in the modern world, in the sense that almost none of the actual implementational suggestions or proposals that are in this paper ever really came to be, because it all kind of went to the left a little bit and then parallel. If you read through, especially the first half, most of the justifications for why you would want to do this, and the conceptual ideas behind why functional runtimes are um, um, attractive for computer science reasons are all here. Basically, like whenever you get into a Twitter argument with some FP guy, all of the things he says are going to be in this paper and were said by Backus in '77 and have been repeated ad infinitum since then.
But the,
With
but they're going to leave things out, right? So the
yeah,
thing I was going to say is,
yeah,
I thought I had read this paper. I
right,
would have told you I'd read this paper. And because it's referenced in the Haskell report, it's referenced in various history of Haskell articles. I
right,
listened to an excellent podcast by Eric Neumann about this paper. And in preparation for this podcast, I actually read it and realized that everything I've read about it kind of only talks about basically the introduction. And
right,
there might be reasons for that.
right. And I think I was thinking about this, and you can kind of draw. So the first piece of background really is to say, well, who was this Backus guy anyway? And so Backus is one of the like biggest brains in the sort of early programming language design space, and so he's he's the guy behind Fortran, among other things. He's the B in BNF. If people talk about parsers, Backus now form is the standard sort of syntax for parser generators and whatnot, and that's him. And he was also on the various algol committees, and so at least up until like the time period of this paper, that he has an enormous amount of influence on how programming languages go. And I think a very analogous figure in a different part of computer science is this guy is Knuth, right? And so Knuth is incredibly influential in algorithm design and whatnot. And everybody knows about his books, but nobody really reads his books,
Well,
which is a hot take. And nobody really does algorithms or algorithm design or studies, the performance of algorithms the way Knuth proposes to do in his books. And so I think this paper is sort of a similar kind of foundational work in language design, except that the what people actually do these days is somewhat different. Which if you get to sort of the middle part of this paper, you'll find out, right? And so and so the question that you might ask at that point is, what are these foundational ideas? And the hint is in the title, this von Neumann model, and like, why do you need to be liberated from the so-called von Neumann model, right? And I think that's covered. So what he means by that is mostly covered in the introduction, where he lays out sort of three three possible ways that you can model computation. The first one being sort of operational, meaning Turing machines, like simple operational models that have been used mathematically in the past, and the best example would be Turing machines. Applicative models, which the best example would be lambda calculus, and the applicative models are based around the ideas that computation is structured as function application, as opposed to what Turing, like a complicated state machine, like what Turing machines do. And then the so-called von Neumann model, which is basically how all CPUs built since the 60s work. Was right. So programs are stored in memory, and you fetch the program from memory and execute instructions that are given to you, and you read and write the results of these computations back and forth to the memory. You're muted.
Sorry about that. What I wanted to say was that my introduction to John Backus was learning both Pascal and Modula 2. In the early 1980s, any book teaching you a language felt obligated to include a 150-page appendix specifying the entire language in the BNF format.
Right.
Which was, I mean, I have to say, I don't know if other people found this useful. I found it profoundly unhelpful in terms of actually learning a language. And it really does say something. I mean, it's more of a biographical note. It's not really about the paper. But
Right.
anyone who you could say about them, they invented Fortran, ... among other things. I mean, that's a heck of a resume.
Yeah. Yeah. So, and there's a reason this paper is a Turing Award lecture. I mean, the Turing Award is sort of this sort of not really a Nobel Prize, more like a lifetime achievement award that the ACM gives out. Um, and so that at least among his peers, he was thought to have achieved a lot in the time that he was working, and that's why I think the at least the conceptual basis for this paper is probably so influential, even if the it doesn't really lay out either the abstract or concrete functional programming language models that actually became dominant. And I mean, for those in the audience who might not know, I think the ones that became dominant are sort of based around the lambda calculus and type systems. And so the lambda calculus ones, the easiest example to point out is Lisp, and the type system world is standard ML and Haskell. And languages that have been built since then, like I don't know, Rust, Swift, Clojure, uh, Scala, etc., are all sort of in that mold with other things on the outside. So, and FP is not any of those things, but why do you want this applicative model anyway? And I think the main reasons that he would lay out are trying to free yourself from thinking about computation in what he calls a word at a time format, basically iterating through memory, right? You want to be manipulating sort of higher level structures and more static structures. And what that also brings up the next thing, which is that the functional programming language doesn't really have any notion of state. And so the program itself, in some sense, and the data that it acts on, in some sense, are static. And this is a big, big, big idea, because that's where the sort of second part of the title comes from, the algebra of programs, the idea that you can manipulate the program code algebraically has always been a big goal in the functional programming world, because they want to be able to use formal systems, so if you can manipulate code in a formal system, then you can manipulate basically what that means is the compiler can do interesting things for you, interesting kinds of analysis that you can't get with or at least at the time, it was thought that it was very difficult to analyze code that has a lot of state or dynamic behavior in the same way.
So when you look at this paper, or not when you look at this paper, when you see people talk about this paper, as you mentioned, functional programming enthusiasts tend to use it as kind of the explanation for why all of our programming should be done with, the typed lambda calculus typically
Right.
is what the most strident folks reference. And as you start looking at the paper, the thing that jumps out at me is he goes out of his way very early in the paper to kind of call out the lambda calculus as, no, I'm not talking about the lambda calculus
Right.
as I propose this model. Can you talk a
Right.
little bit about that?
Um, yeah, I know. I noticed that. I hadn't noticed that before. I sort of wonder what his motivation for that was. The hint is that in one of the early sections, um, he characterizes the substitution. So, lambda calculus uses this sort of substitution model
Keep going.
for modeling function applications. So, if you apply a lambda expression to a set of arguments, what happens is that they get Macker expanded in the body of the lambda expression, and then you recursively run the evaluator down through the expanded expression. And the only motivation that I see in the paper for avoiding this idea is that it's more complicated than not doing it. So everything that he is doing in his simpler functional programming model doesn't have this substitution rule. And I didn't actually read through the more abstract parts in the second half of the paper so that I can talk about it off the top of my head. But if you go through the evaluation rules for his FP, that that sort of higher order behavior in the lambda calculus isn't there. And so I think really what he's doing is he's trying to make his base language even simpler than lambda calculus.
Well, to,
But it's not clear to me exactly that it's not 100% clear to me that that's really what he's going after.
well, to put not to put too fine a point on it.
Yeah.
When you get to the second half of the paper, starting right here, this is actually a bit early. I have a note where I said, I'm not going to lie, my eyes started glazing over at this point. And you know, I'm reading the paper, I'm taking notes, I'm kind of noting things. And then you get to that back half, and it's very dense. And the analogy that you made when we were talking about it was really to APL more than almost anything else.
Yeah, definitely.
And
It's definitely very much like APL
it's
in the sense that he wrote all that code and nobody else can read it.
it really is. It's write only code. The the other thing that is interesting to me, and this is not meant as a criticism, particularly in the beginning part of the paper where he's rolling out the idea of, well, you know, we're doing a disservice here because we're not actually, well, I don't feel I've actually introduced the rationale here. And for me, the meat
Right.
of it is really where he, let me get the paper on screen here. Not that people on YouTube can read it. He gives these kind of three options, right? One of which is simple operational models, which is kind of the Turing machine model, and he explains what's wrong with each of these models. So for truly, you know, Turing machines, what's the problem with them? The programs are unclear and conceptually they're not helpful at all. He talks about the applicative model, which is really lambda calculus here, pure Lisp as an example. And he describes programs can be clear and useful, but there tends to be problems with storage. They're not as stateful, right? Which is state is useful. It's why we use it. And then he talks about the von Neumann models. And under von Neumann models, I think he's really trying to group almost all imperative language, all imperative programming.
Yeah.
Is that fair?
So,
Really, Algol and its children. And what and his example here is programs can be moderately clear, are not very useful conceptually. And the semantics of what he calls the von Neumann model is state transitions with complex states, which is fair. If you've ever written a large program, there's an awful lot going on.
right.
What I wanted to call out really is what level is he operating on here? Because if you or I are looking at computers in, when's he writing this paper? 1975, 1976, 1977. I would say 1977, you're just beginning to have computers of sufficient power and expressiveness that you could imagine. Let's make a programming language that's going to be used for, real work, that is not strictly a load store machine,
Mhm.
or dealing with assignments. And so I want
So,
to
so
criticize
that's
him
you
about that, but I
mean
don't know if it's fair, because maybe he's operating on, he spent years writing Fortran, Algol, so his head is on a different level of abstraction than maybe other people were working on at the
right?
time.
Yeah. So the feeling that I had about I think you're right in that we're not giving him enough credit because we're looking at this paper with almost 50 years of retrospective work in functional programming systems. Um, and in some sense, we're criticizing it on that platform, which is not a fair thing to do. What you should be doing is what you have to be able to do to really read this paper in the actual context in which it was given is sort of roll back all of that and imagine a world where um, essentially the major languages are C, Pascal, and Lisp, right? And there are a couple of things going on at Xerox Park that are a little bit more interesting than that, but not really. And so the I think what he's sort of getting at in those three models are like the most formal and mathematical model for computation at the time would have been like the Turing machine stuff, or um, even simpler state machines, right? So finite state machines up to Turing machines are what they would teach you in theory of computation, right? Um, the applicative model is obviously Lisp, um, because it's that was sort of the only major player at the time. And the imperative model is basically everything else, or the von Neumann model is basically everything else. So any language that is essentially based on an execution model, which is just an abstraction of a typical hardware CPU. And pick your favorite one, VAX. Although VAX didn't exist yet, so PDP-11. Um, and I think the interesting thing about this paper, in the context of the way we think about these things today, is he's really he's not really talking about programming in the large the way we would think about programming in the large now. Like the the biggest programs you could possibly think about writing at the time,
Compilers, right?
right, would have been maybe compilers, something like tech, which famously is sort of one source file that's a few thousand lines of code, and that's thought of as pretty big, right? And so I think you're right in that the sort of abstract model of how programs are structured is kind of different, in this context. And we're not quite in a world yet where something even as relatively large as the operating system would have been. I mean, operating systems were a thing that multiple people would have worked on, right? But it's also probably possible in that world, to for like two or three people to write an operating system and have all of the code in their head, right? So the early Unix kernels, I bet, were along those lines, right? Um,
And
and I think,
just to interrupt,
yeah,
complexity was something that people were wrestling with. Dijkstra famously introduced the idea of, you and I are so, really hideously old, that we predate object orientation, and the thing we
right,
talked about was structured programming, where you're going to
right.
break things down into procedures, not functions. It might be functions if you're a weirdo, but probably just procedures, just breaking it into more steps.
Yeah, and even you have to imagine a world where even something like an idea like a module system or separate compilation was a relatively novel thing. Like being able to actually write your code in multiple source files and glue them together later was not routine practice, right? And so you certainly couldn't do it in standard Pascal. You could do it later in Modula and Modula 2, but those were in the 80s. Those weren't now, right? And so I think you see this most in the later parts of the paper where he's proposing these functional programming systems, which would be completely and utterly, what's the word, inadequate for actually dealing with large amounts of code, right? But the motivation for starting with this basis is still you want to be able to build code on a basis which is sort of static enough that it lends itself to algebraic and static analysis. And that's really, I think, the really the big motivations in this piece are that, which is still like the main one of the main justifications for people wanting to put up with all of the other weirdness in functional languages. And also this idea that you should be able to structure programs around the manipulation of aggregate structures with composable operations, right? So the composability is a huge idea. Um, and the interesting it's sort of interesting to me that he looked at the world and he wanted those two things and he picked APL, right? And so I don't really want to drag him too hard because the context in the context it kind of makes sense, but it's also very interesting to me that certain obvious moves here are completely missing, right? So um, fighting complexity with something like modules is completely missing, even though it later it comes up in actual functional programming systems like ML and Haskell. Um,
Well,
more
as you observe, though, I mean, programs were generally not big
right,
enough, right? Like when Modula 2 had namespaces, essentially,
right, right,
people were upset about it. People are like, "This is why is the language getting in my way and forcing me to
right,
organize all this
right.
stuff?"
Another thing that never turns up in this paper is more complicated data types, right?
Or
All he has is arrays and lists,
yeah, not even sum
right?
types or algebraic data
Um,
types at that point.
and then what was I had another note, right? And the main criticism in this paper about the von Neumann computation model is he's constantly harping about on this sort of word at a time style, and again, that's kind of true if you push it all the way down to the lowest level implementation. But imperative languages with higher order type systems, mitigate that to some extent, and you see that in modern languages like God forbid C++, but certainly Rust, Swift, etc., where you are combining the sort of higher order type systems with more traditional imperative programming models and getting some amounts of leverage that way.
Let's dig in on this a little bit because
Right.
I think it's worth talking about. You're correct that what he's really kind of I don't want to use what he's really addressing here, or bemoaning. I think it's fair to say that that's not an
Mhm.
insulting word. Is the primacy of the von Neumann computer, but I don't think of the essential element of the von Neumann computer as being the fact that it deals with things a word at a time. The major alternative to the von Neumann computer at the time architecture that I'm aware of was the Harvard architecture. In the Nan to Tetris course,
Mhm.
lots of other things on this channel about that. You actually build a Harvard architecture computer, and the key idea there is that your program store is not in the same memory space essentially as your data.
Right. Right.
And so I never really get to the point where I understand the alternative, and I am aware that later years, like in the early 1980s, there was thinking machines and the Lisp machine. And my understanding as a very surface level is that these machines were architected to be more amenable to
Yeah.
Lisp specifically, but functional. How much can you shed any
Yeah. So
light
I
on that?
know I remember a little bit about this because it was a big thing when I was in grad school, where these hardware architectures for specifically executing functional programs. Again, it's not Backus's FP. It's also not really lambda calculus. Instead, there was a lot of work on hardware to execute combinatory logic. So the SKI combinators and all that, which if you know your logic and programming language theory, you know that you can translate lambda calculus into this fixed set of very simple they call, I don't know why they call them combinators. I don't know the history behind the term, but very, very simple functional primitives, and then base everything off of that. Those machines came out of the data flow work. So data flow was this idea that instead of building this sort of load store kind of architecture, you would build an architecture that essentially computed everything as needed. So, Haskell in a box or something like that. And then the idea would be that the parallelism of the execution is limited only by the actual data dependencies in the code, assuming that there aren't any side effects. And so then you go full circle. You write in a programming language that doesn't allow you side effects or dynamic state. You compile it down to some sort of hardware language which is based on just the raw data dependencies as opposed to manipulating state. And then you can run these then the hope is that you can run these computations with a high level of parallelism. And so there was a lot of work on that. Also, I think it. I stopped looking at all of this probably in the '90s after I got out of graduate school, and I think coincidentally, none of this stuff ever really made it to delivery, right? And so there were a few highly parallel pieces of hardware that got pushed into scientific computing um, in the early '90s, like connection machines,
Well, I
a
mean,
few other
there
things that
there
nobody's
were
heard of.
specific domains where
Yeah,
these
yeah,
ideas took hold. The one that
right.
really jumps out at me is HDL, hardware description languages. Do in fact, they're not lambda calculus, right? They express things functional. They are declaratory. Is descriptive the word I'm looking for? Descriptive, I think. That is an area where people's first experience dealing with Verilog or VHDL is
Right.
is they it if you squint at Verilog, it kind of looks like C, so I'll write a C program, and of course it doesn't actually work that way, and it surprises them. So there are
Yeah.
domains where it took hold,
Yeah,
but
and
not
actually
the general purpose computer.
I'm also leaving out all the work in logic programming. So logic programs sort of lend themselves to this sort of data flow kind of idea. Um, but nobody likes Prolog, let's be real. So
I never took a Prolog class.
yeah, and
I
it's
did remember
hopefully,
people complaining about the Prolog class.
yeah,
So
it's hopefully mostly forgotten. Prolog is the champion language along the measure of how much you can mess up your code by changing one character in the program in the wrong place, and
can
only.
can I
um,
take us on a tangent?
yeah, yeah,
He talks about Turing machines being unusable and you know that you can't run a program. And this sparked a memory with me. I think it was one of these like implanted memories of using a Turing machine simulator in the
mhm,
late 1980s. And I went and looked at it, and I found it. It's called Turing's World. It was made by a couple guys at Stanford. In the recorded version of this video, I will put an insert here. However, I cannot for the life of me remember what class required me to develop Turing machines with a simulator. And
um, so if you were on the same kind of track as I was at Carnegie Mellon, it would have been 211.
that tracks. That
Yeah,
makes sense. Yeah.
because
That also explains
that
why
was,
I've blocked it out because it
yes.
was all.
Because back in the day, that was the theory of computation. They
211
were,
was Theory of Computation, Data Structures and Algorithms 1,
yeah,
I think. It was
yeah,
the name of the
that sort of
course.
thing. Anyway, um, yeah. So there was all this work which you can probably still look up in the older literature from 87 ish to 92 ish, and Paul Hudak, actually, one of the Haskell guys, comes up in this a lot because he worked on a thing called the SECD machine, which was probably the closest thing to something that somebody actually ever tried to build, that was based on this idea of executing combinatorial logic. I think the key words to Google for are graph reduction architectures, because when you compile functional programs to these combinators, you get a sort of graph the data flow graph of the combinators, and the idea is that you're performing computation by reducing that graph down to the single answer or whatever it might be. And the interesting thing to me is that these sort of never went anywhere, and the highly parallel architectures that we actually ended up with in the world were either the giant machines that just do matrix multiply, that the Defense Department uses to simulate various things, and GPUs,
Hmm.
right? And GPUs are also basically just tiny little von Neumann machines replicated billions and billions and billions of times,
Doing a
right?
lot of matrix multiplication.
Doing a lot of matrix multiplication. And so I think the thing that he sort of maybe in retrospect, the thing that is missing is the paper assumes that there are sort of very, very interesting things to be done specifically in the sort of parallel computation and high performance area, that functional programs, or maybe all of this work on parallelized functional programs, was making this kind of assumption. Is making this assumption that there are more interesting things to parallelize in the world than matrix multiplication. And it turns out that's not the case. The only thing people really, really want to run really, really, really fast, and are willing to deal with weird architectures to make it happen, is something analogous to matrix multiply. And there's a lesson there somewhere, at least an engineering lesson. So,
Now, the latter half of this paper, as I said, I anyone who discusses this paper almost always only talks about the first half
right.
or just mentions it because the title, you can take that title and of course, as John Backus said in his
Right.
can programming be liberated from the von Neumann paradigm? The fact that it's not proposing your paradigm can be completely ignored. There is an area that I think has been becoming more, it's certainly become an area of more interest recently, but even back in the 80s it was a thing, which is proof systems,
Mm-hmm.
right? Functional programming using, is it the Curry-Howard isomorphism? I'm forgetting. Is
Yeah.
that the one where
Proposition those
proposition
types.
types, right? And he does go into this a little bit, and has an entire section 12 and onward is kind of where this paper gets into what I would describe as the hard going. It's the
Right.
algebra of programs for FP systems.
Right. And again, what's interesting about it is that it doesn't have anything to do with lambda calculus. So the like the highest level, um most blurry sort of history of functional programming that you can provide is sort of, first there was lambda calculus, then there were people working on these automated proof systems, and that's where all the modern programming languages came from, right? So Haskell sort of has this background because all the people that worked on it were sort of at least tangentially in that kind of logic area, right? ML actually was literally the meta language for a proof system, when it was originally created. And so there's this whole other this whole other tree of thought around type lambda calculus and type theory and the fancy type theories leading to programming systems, is something that this paper essentially doesn't land on at all. And so my high level reading of the stuff that he does talk about there's sort of two main things. One being um, examples of how manipulating pieces of static code algebraically can have some utility, in that you can prove things about what the programs are going to do, at least on a very small scale, um, sort of purely formally, I guess,
Mm-hmm.
is the way I might put it. And then I guess the last section is also sort of a meditation on how to deal with the fact that any kind of programming system that you build is actually going to have to deal with dynamic state. And so he has some proposals for doing that, but they're pretty rough. And later on, the solution that people would end up coming to is the cursed monad thing. So if you actually want to deal with state and purely functional programs, you do what Haskell does. It's a very elegant solution. It has reasonable mathematical foundations, and my relatively shallow reading, what Backus is doing in this paper is he's basically creating an FP program structure that just carries the store around as a parameter to
Right.
everything, right? Which is what the state monad is eventually going to do, except that you don't have to do anything by hand.
Right.
The state monad does all of the wraps the whole world just the way you need, right? So again, I think you end up, for me, you end up sort of in the same place. He has all the ideas correct and lined up right, but the way you would actually implement them turns out in the real world to be completely different. And I don't think necessarily you should take away any credit for that, because nobody really knows. Nobody can really predict how things are going to turn out later. Nobody would have predicted in 1980 that C was the thing that would take over the world,
Hmm.
right? Because C is terrible. Um,
At the time, Pascal was, I mean,
yeah, yeah.
Pascal was a real thing.
So, and so similarly, you wouldn't, it's not as obvious, then as it is in retrospect, that the lambda calculus is sort of the right foundation for all of this, or the type lambda calculus is the right foundation for all of this. And so I don't think you necessarily take anything away from this paper, by noting that he didn't end up there. If he had ended up there, he'd be a real genius.
I do think that you could probably break people's brain
Yeah,
by even saying that, like, yeah, there's functional, you can do functional programming without the lambda calculus, like, and it's
right.
really not the basis of it. It's one way of doing this, and it's a useful way, and it doesn't
Yeah,
take anything away from it. But
yeah. I
um,
think that's definitely true.
there are some. Uh, this is a bit of a tangent, but it's so interesting. There are some great videos of Alan Iverson back at IBM introducing APL. Is a video of him introducing APL in black and white, which is weird because they had color film then. I don't know why they filmed it in black and white. Um, and it was very clear that he approached this as kind of, an algebra problem. That's really what his intent was to create. Here's a tool that's going to let you use the computer for algebra, because that's what you were using computers for, is algebra, right? Essentially.
Yeah. Actually, there was a thing back in the day, even when I was at CMU, it already existed, called Maxima. It was built
Right.
at MIT, in the Lisp systems of the day. That was one of the first computer algebra systems, and so
A
the
precursor to Mathematica, not in a
yeah, not I mean
parent-child way, but
same kind of idea, Mathematica, MATLAB, all that,
Maple.
Maple. Clearly, those systems do a ton more. Um, I think I only ever I played around with it. I think I probably used it in a robotics class once to do some terrible linear algebra computations or something. But anyway,
Is there
um,
something we can learn here about the nature of writing papers? Because this paper, if you go to the ACM, has 1,900 citations, roughly, a little
yeah,
more than that. Most of which, I'm going to be honest, I did not look at half of the 1,900, so I'm kind of spitballing. But everyone that I kind of spot checked uses this paper for nothing more than kind of a hand wave about, well, functional programming is really great and better than imperative, as John Backus talks about
yeah.
in his
I
seminal
think
paper, without ever kind of taking
yeah. I
the
mean,
work that he put into this.
I muddled through this a little bit at the top, right? The influence of this paper is almost purely conceptual, in the sense that it lays out it lays out the three or four arguments that you want to lay out to try to convince people that, the functional style has some utility over the imperative style, as it were. Um, and those four arguments since 1977 have been relatively unchanged. And the extent to which they're relevant or not is sort of also relatively unchanged. Like basically, if, yeah. And so I think I think what the citation count represents, or indicates is not necessarily anything about the content of the paper, but more about sort of how academia works, right? So this came out at a time when research in functional programming was just getting started. It is conceptually foundational. So everybody that writes a paper, an ongoing paper or a newer paper about the same ideas has to backcite it.
Mhm.
Um, and eventually it just becomes sort of a reflex. You backcited what you will backcite it even if you didn't actually necessarily read it, just because you have to backcite it. Otherwise, it's like it's a socially awkward situation because this is, in some sense, it's in some sense like writing a paper about a complicated analysis of sorting algorithm without citing Knuth Volume 3, right? Even if you've never looked at Knuth Volume 3, you have to cite Knuth Volume 3 because that's where all the material came from, right?
So, so,
Um,
so it's an influential paper. I have to
yeah,
ask,
definitely.
if you were to pick, say three other papers that you felt were of similar import, what would you
Oh,
zero in on?
in any other
In
area or
in
in this?
computing specifically.
Oh, I don't know. I mean, I haven't been in academia for so long that it's a tricky thing to say. I have um, in a similar area, the Guy Steele paper about go-tos, like Lambda, the ultimate go-to, which eventually turned into all the continuation work and whatnot. At least at an implementation level, I think is sort of similarly influential in a lot of ways on a conceptual level. Um, in systems, a lot of the early Unix papers probably, because everything became Unix eventually, and so then you can't escape thinking about the world in that particular kind of way.
Mm-hmm.
On the other hand, all of the stuff that came out of Xerox PARC about nominally the same kind of problems, right? How should programming systems be structured? And what should the user interface look like, right? Those, especially the Smalltalk ones, have had an incredible amount of influence on how actual consumer software is built. But I would bet that the papers themselves are almost completely forgotten. Like
We
you
have a
may or may not.
we have a comment from one of our viewers, a Tom,
Yeah.
who says the takeaway is that if you want to boost your citation count, it helps to win the Turing Award.
Yeah, that's always true.
All of
Um,
these Turing Award, by the way, these Turing Awards, they all people who won them, at least in the 1970s, I assume it's still going on, gave speeches, many of which were based on papers, and
mm,
they're all good. That would be my kind of go to, I guess go to, would be to pick another one of those and talk about it.
yeah. I mean, the other thing that we were going to do in this video before we got landed on this was to talk about the Larry Tesler article in the Byte Smalltalk magazine about the Smalltalk user interface paradigm, which is basically how every single Windows system has been built since that article was published. Like all of the text editing systems you've ever used, except Emacs and VI, that were built since then, like everything they did at Xerox, Windows, Mac OS, Next Step, everything is in that article. Um, Even iOS, except they had to translate it into touch, right? But it's the same kind of basis. So
We'll
yeah,
get to
and
it. We'll
I have a soft spot for the Park papers, but I know that I think they're hard to find, and I don't think people necessarily really read them anymore. Like
Mhm.
the stuff about Mesa in particular. So
Actually, I want to go back. I know I feel like we've kind of talked through the big points here that we
yeah,
wanted to
definitely.
cover, but he does name check Dana Scott, and I had asked you when I saw that. I said,
Mhm.
"Wait a minute, Dana Scott, Dana Scott." I walked past that guy's office, but I don't know what he did.
Oh, so
Can you refresh my memory?
yeah, so Dana Scott is big in logic. So he's done a lot of work in logic and a lot of the ideas that lead up to and are related to things like propositions as types. And so um, I think if you do any amount of deeper reading into um, sort of the current type theory work, or where the current type theory work came from, and things like homotopy type theory, and other esoterica. His name will come up over and over and over again. So he wrote especially in the 70s and 80s a lot of influential papers, basically in computability and logic. So a lot of meditations on lambda calculus and what it means, and various other things related to that. I'm not intimately familiar with any of the material per se, but he's a big name. Um,
I'd like to start closing this down. I feel like
yep.
we've talked about it, and one of my favorite topics really is terminology, and we very often use very amusing terminology in when we're talking about programming, and very often I think it's unhelpful. And I'm throwing on screen here a tweet that our friend Patrick did. It says, "I love to use footnote dependency, footnote injection, which is and the footnotes are pass values to function."
Right.
I've been trying to understand with respect to homotopy type theory. Is it I'm not sure how to
Homotopy.
pronounce it. Homotopy type theory. I've been
Mhm.
trying to read up on it because I thought, oh, that would be a really interesting
Oh,
video. And I feel
that's a
so
really,
much
really,
like little baby who is completely unqualified to
yeah.
discuss it. But really, where I was going with this is I thought of a good segment because I'm going to have you on again. You're going to be here again.
Okay.
And so every time you come on, I want you to define, I want you to tell the world, because this is the most popular thing, what's a monad? And then every time I need a different, I need a different analogy. So what's today's?
Oh, monad is a burrito.
Is that your favorite?
Yeah, that's my favorite one. You can Google for the paper. It is exactly correct.
We have another comment from the comments. Over the last decade or so, Dana Scott has been on a roll of lectures, all in video online, about lambda calculi and their history from his own personal perspective. Highly recommended. Thank you very much, LC. We will check that out. I also wanted to signal boost a paper that. So here we have a link to the paper at the ACM. Eric Neumann did a podcast where he talks about this paper, "Can Programming Be Liberated from the von Neumann Style?" in great detail, and it's a little more structured. I think this is just you and me,
Yeah.
talking about it. But I do recommend his podcast. He covers a number of these Turing Award lectures, and I just didn't want to do this without giving him the shout out for doing really interesting work.
Cool.
Pete, I'd like to thank you for coming on. This was really great, and
All right.
I hope we can do this again, and I hope we can do it again sooner than 6 months.
All right. We'll do Guy Steele next time.
Sounds great. Thanks, everyone. This has been Programming Like It's 1977. Thanks for watching.